So we're going to talk signals and emissions. 3 more exam questions. So we'll do carriers and modulation, talking about AM, FM, single sideband, a little more detail than what we just went over. Examples of digital modulation and overmodulation for AM and FM, frequency mixing, frequency multiplication, which is used for normally in FM transmitters. Bandwidth. I think we bring in Carson's bandwidth rule, duty cycle intermodulation, and digital emission modes. So let's start with this nice little video. Modulation is one of the most frequently used technical words in communications technology. What is it? Communications technology. Frequency. We had frequency of sound. The antenna size required could have been in the range of kilometers. This is why we need modulation. Before the transmitting, they should be modulated to a high frequency signal. We can understand. Try throwing a piece of paper. Now tie it to a stone. And the second method is obviously more efficient than the first one. This is in place of a stone, modulation uses a high frequency signal known as a carrier signal. As we know, any signal has 3 basic properties: amplitude, frequency, and phase. In the modulation, therefore, the frequency of the carrier signal is vary according to the amplitude of the message signal. It's known as frequency modulation. Please note that the value is the modulation. So that's high and low amplitude relates to 0. The next technique is zero based on the value of digital process, the frequency of the carrier signal is adjusted. In this case, high frequency. The So practically set up this thing. Of QA is that you can modulate these two different signals as a single signal and then transmit it. Then at the receiver end, you will be able to separate them, thereby bandwidth. Let's see how this modulation is done. In QAM, the first signal is amplitude modulated using a carrier wave as shown. The second signal is also amplitude modulated, a carrier wave of the same frequency and amplitude, but after giving the carrier signal a 90-degree phase shift. Now, these two modulated signals are mixed together to form a single signal. We call it a multiplexed signal. The interesting thing is that on the receiver, separate out the original signals from the multiplexed signal. In the case of digital QAM, a similar approach is used. The combination of bits are added together. Let's values of conformities. Since I will have different layout, such 16-bit values can be represented by adjusting the phase and amplitude of the multiplex signal. And this are the different values signals represent market or business value. Using a the revolving phase by 90 degrees used. Hence the field instead of Q. Thus, scientists one of the okay. Okay. Wasn't that interesting? So the one thing I noticed in there, and they never mentioned, but essentially they were talking about I and Q signals when they talked about the quadrature and the 90-degree phase shift, like we were talking about before with the SDR radios. So here we have three representation of three types of modulation: AM, FM, and digital. Same kind of waveforms they were showing in the video, where you're either changing, in this case, we're changing amplitude, we're changing frequency, or in the digital modulation, this one would be frequency shift keying because it's changing the frequency. It could also be phase shift,
keying. And most of the digital modes will use either frequency shift or phase shift keying. So amplitude modulation is varying the instantaneous power level of the RF signal. And you get this envelope, okay, which is on the receiver, what you're actually going to detect and convert back to audio is what you hear. And that's a representation of the voice modulation waveform at the transmit. So what type of modulation varies the instantaneous power level of the RF signal? I can't say illegal. Amplitude modulation. I think they word it that way to confuse you, where the power level is basically you're modifying the amplitude, which in effect changes the power level. Okay. Modulation envelope of an AF signal is the waveform created by connecting the peak values of the modulated signal, which is what the blue line represents down here, is this envelope, which is proportional to the modulating signal. So what is the modulation envelope of an AM signal? Come on, wake up, John. Wait. Yeah, that's what I was saying. Connect the peaks of the modulated signal. Single sideband. It's a form of AM modulation that uses only one of the sidebands. For normal AM, you're going to get the carrier plus two sidebands. They're mirror images of one another. When we do single sideband, we get rid of a sideband and the carrier. Single sideband is the narrowest bandwidth of all the voice transmission modes. And that's even true for digital. There's an effect called flat topping, where if you're modulating signal, you talk too loud, too close into the microphone, for instance, or you have too much microphone gain, you can actually cause the signal to the peaks of it to be clipped, which is why they call it flat topping. And that causes a lot of harmonics, and you get a lot of signal distortion. Which of the following phone emissions uses the narrowest bandwidth? What is meant by the term flat topping when referring to a single sideband phone transmission? And that would also be true for AM. You have the same problem. Overmodulation. Okay, when you're modulating at more than 100%. Okay, in the three graphs there, they're showing 50% modulation, where you're changing the amplitude by 50%. The middle one is showing 100%, where you're basically changing the carrier from its maximum amplitude to 0 and back. When you have overmodulation, and they're showing 150%, you wind up in these crossover regions with a distorted waveform. So if you look at that envelope, what you're going to detect is something like this, which does not represent the modulating waveform. So you're going to hear a lot of distortion and even some harmonics and other spurious frequencies. So on FM, okay, you have a similar problem. If you overmodulate, since in FM you're deviating the carrier frequency, you're going to get, and it's proportional to the amplitude of your modulation signal, you're going to get over deviation. And typically for broadcast FM, the deviation is like plus or minus 75 kilohertz. And that's why the stations are separated by 100 or 200 kilohertz apart. In amateur normal FM, we use a 5 kilohertz deviation, and the spacing is going to be in the 15 to 25 kilohertz range. And for narrow band FM, we're down to half of that, which is 2.5 kilohertz. So you can get smaller bandwidth and closer spacing, more channels basically in the same band. The little chart here is showing the typical deviation about the carrier and what the peak deviation is, and you're supposed to stay within that range. So which of the following is an effect of overmodulation? So frequency modulation is defined as the process that changes the instantaneous frequency of an RF wave to convey information, where AM changed the instantaneous power of the RF wave. So again, like in the video, you see it's changing the frequency depending on the amplitude, whether it's positive or negative. What is the name of the process that changes the instantaneous frequency of an RF wave to convey information? Delta, frequency modulation. Phase modulation changes the phase angle of the carrier signal. You can do it with what's called a reactance modulator, which is frequency and phase sensitive to voltage. So that gives you a varying either phase or frequency change with the input modulating signal. What is the name of the process that changes the phase angle of an RF signal to convey information? Phase modulation. What emission is produced by a reactance modulator connected to a transmitter RF amplifier stage? They don't list frequency in there, so it's just phase. Okay, frequency shift keying. Some of the digital modes use FSK. FT8, one of the most popular ones currently, uses FSK, and they actually use 8 tones. In this one, we're showing direct binary FSK, which is each symbol that is sent is representing two binary bits or four states. So it can be 0, 0, 1, 1, 0, or 1, 1. And in the case, and that would, each of those states would be a different frequency. So you discretely modify the frequency in steps depending on what the value, the binary value is. So you'll have four different tones that you can send. If it was FT8, there's 8 tones, so are 8 states, and they're each one is 6.25 hertz, so they vary over a very narrow range. How is direct binary FSK modulation generated? Yep. Change the frequency directly with digital control signal. Actually, you don't even necessarily have to modulate the signal. You can synthesize those tones directly. In what they're calling quadrature phase shift keying, which is one of the modes of phase shift keying that's used by some of the binary or digital modes. And BPSK31 is one of the older, more popular digital modes. The 31 comes from the fact that it's a 31 baud transmission rate. It gives very narrow bandwidth. Forgot what it is, but I think it's down. Is it 250? I don't remember, but it's relatively narrow. Not as narrow as FT8, which is 50 hertz. There is some forward error correction. Wow. Because of the extra bits that they send. So basically they send duplicate information or some duplicate information. So on the receiving end, you can see whether or not the checksum agrees or not. And in some cases, correct some of the errors. Most of these digital modes work in upper sideband. It's just a convention, but you have to match. So if you're transmitting upper sideband, the receiver has to be in upper sideband to receive it. So that's kind of the standard is to use upper sideband for these digital modes. And in this case, with the quadrature, each symbol is representing 2 binary bits. So you got 4 states or 4, in this case, 4 different phase shifts. If this was quadrature frequency shift keying, you'd have 4 different frequencies or tones. In this case, you're shifting the carrier wave by 90 degrees. And they're starting off at 45. So you've got 90-degree phase shifts that represent each one of the states. This is kind of what, well, this is what a binary phase shift keying envelope looks like. Not that it means a lot. So what is quadrature phase shift keying modulation? He refuses to use the phonetic alphabet.
I thought that's what he said, but no.
It just wasn't quite like another shirt one. So it uses four different phases to represent the pairs of bits. Um, I don't know what, let's see, quasi-parallel to serial conversion. No idea what that is, even if it's real. And quadrupole sideband keying to generate spread spectrum. Actually, I don't know how they generate spread spectrum. I looked into it a little bit, and I don't think that's how you do it. And we don't use fast Fourier transforms to do these. So which of the following is characteristic of QPSK31, which is one of the modes? Okay, three of those today.
I got one all right.
So it's all the above. You have to match the sidebands. There is some error correction embedded in the messages, and it's approximately the same bandwidth as binary phase shift keying. Okay. WSJTX is a software suite developed by Joe Taylor. He's a Nobel laureate for his work in deep space communications with very weak signals, which is how this amateur stuff came about. He's also an amateur radio operator. And that suite of software supports, I don't know, 10, 12 different modes. There's the most popular ones of the group are FT4 and FT8. FT8 is the most widely used. It uses 8 tones. FT4 only uses 4, so it's a quadrature. There's JT4, JT8, 9, and 65. I played a little bit with JT8, and their messaging formats where you actually type. JT65 is the one I understand is most commonly used for moon bounce, meteor bounce. I don't know anything about Q65. The MSK44 is typically used for meteor scatter. So we get into that stuff when we talk about propagation and things a little bit later. And then there's the whisper and echo modes. And whisper is weak signal propagation reporter, where it sends out, you can set up what they call beacons that transmit in whisper mode, and they send out location information, propagate, signal strength, some things like that. So you can kind of tell what the propagation is at different frequencies and coming from different areas. They also use that on these balloons that they send up and track. Little micro balloons that can sometimes they're able to go all the way around the Earth several times before they come down. Sometimes they don't make it past launch. It depends on the weather and a whole bunch of things. It's pretty tricky. I went to a seminar on it. It was quite interesting. Might try it sometime, but it's about probably cost you $100 to send one up, and then may or may not go very far. Well, they're pretty small, only 2 or 3 feet in diameter. We don't shoot down the big one. Why would we shoot down the? Okay, FT4 uses 4 tones of frequency shift keying. FT8 was another one protocol that came out of the deep space stuff that Joe Taylor did. These were co-developed by a guy named Steve Frank and Joe Taylor. It uses 8 symbols that are 6.25. Each symbol is 6.25 hertz, and they go all the way up from 0 to 43.75 hertz. So it represents 3 binary bits. So each symbol that you send is sending 3 bits of digital information. The technical thing is it's a Gaussian filtered constant phase, constant amplitude, frequency shift keyed signal. And all that really means is the information is contained in the frequency shift. There's no amplitude or phase variation. And the Gaussian filtered is some technique they apply to sort of round the corners of the waveforms to lower the harmonics and distortion and make it easier to decode. You can receive signals at extremely low signal to noise ratios. Your normal signal to noise ratio is going to be a positive number. This can detect signal to noise ratios of minus 21 dB. So it means that the signal is 21 dB below the noise level. It's amazing. Okay. And here, BPSK is 50 hertz. And this is the same, it's 50 hertz wide. Whisper, which I talked about, is the weak signal packet reporter. Sends call sign, a grid locator, and whatever the transmit power is in dBm. It can be decoded at signal to noise ratios of minus 31 dB. That's 1,000th of a milliwatt. It's actually slightly more than 1,000th of that, 1,000th of a milliwatt. And it's in a 2,500 bandwidth band. And these digital modes like FT8 and the others, basically capturing everything within a normal IF passband, which is like 2,500 hertz for a wide club. So you see every signal in there, and it tries to go through and decode them. So you can also, if you've got the right internet access, you can upload some reception reports. There's a database that keeps all that information you can look at and see what's being received from all over the world and kind of get an idea what the current propagation is for different frequencies. What type of modulation is used by FT8? Okay. These are new questions added just for this year. Link margin and link budget. Link margin is the difference between the power level of the signal that you're receiving versus the minimum signal level required for you to actually hear the signal or decode it. So if you had a system with a 10 dB link margin, that means that your signal is coming in 10 dB more than the minimum you need to actually detect it. So that's your margin. As you get some attenuation of the signal, the propagation changes, whatever, more noise, then you lose part of that link margin, but you've got 10 dB to work with, or a factor of 10. And you can still operate. So what is link margin? Okay, we have link budget. This is how you determine, you kind of determine what your link margin is. And you essentially add up all the gains and losses of a system, which is your path. So let's say you wanted to do moon bounce. Pretty tricky stuff, turns out. I've a friend that does it. He's got quite a setup. Seems like an awful lot of time and money to say hello, hello. But uh, in their little example here of the equation, you take the transmit power. So let's say you're operating at full uh, maximum power, 1500 watts. So that's 61 dBm. You've got uh, really long, 20 some odd element Yagis. Let's say you got 20 dB a gain. You put four of them up, you're up to 26 dB gain. So, and you get to count it again on receiving. So I'm now up to 92 dB gain on top of my 61 dBm from the transmitter. So I've got what? I'm not good at math in my head. We're a little over 100 and something, maybe. Um, I might have some losses with coax and other things, so you knock off a few dB. Okay. But then the big loss is the path loss, which you got to figure from point A to point B, in this case, back. The path loss to the moon and back is 251 dB. So you've got to have a receiver that can receive a signal has a sensitivity of over 100 dB in order to even hear it. So that's why they typically are, most of the things are done with some of the digital modes where you can get a signal noise ratio that's negative. And one of those modes in the WSJTX suite is called Echo, and it's set up specifically to do a test, and it sends something like an FT8 signal or 65, and it's set up just to receive the same signal back to see whether or not you actually can receive your own signal from something like a moon bounce or meteor trail or something like that.
I have to laugh at the antenna polarization loss. I got called up to Fargo, North Dakota because the VHF, UHF repeater for public safety would not pass signal strength. And I went up on the roof and they had a nice little Yagi horizontal shooting to vertical 10 miles away. The minute I rotated the antenna, we picked up about 30 dBm signal strength.
Yeah. Polarization makes a difference.
The idiot that mounted the antenna had no idea.
Okay, so what is a link budget?
Financial costs for something. Yeah, I was going with that.
It takes a big budget to do it.
Oh, no.
Yeah. It's the sum of all the gains and losses around the path from point A to point B and back if you're doing like a bounce. Okay.